Geometric transformations with matrices. All right, transformation is a change made to a figure. The transformed figure is called the image. The original figure is called the pre-image. The translation is the transformation that slides a figure without changing the size or shape of the figure. So transformation, it's just changing the figure in some way, shape, or form. Several transformations that we're going to do. The first type we're going to do is a translation. A translation just slides the figure around the graph, all right? So there are transformations that will flip it and, reverse it or even stretch it or shrink it. But a translation literally just slides it around the graph. And so one way to do these transformations is to use matrices, to set up your XYs in a matrix and then use how you're moving it to add or subtract, in this case with a translation. And so when you have it and they want you to use it with matrices, you are going to set up a matrix. So your first step here is to set up a matrix. And when you do this, you do an X and a Y. So with your coordinates, you're going to say 0, 0, and you're going to set up that coordinate there. -1, 4, set up that coordinate. -4, 2, and -4, 0. And so that is your matrices for this particular quadrilateral. And you'll see that it was quadrilateral A, B, C, and D. Use a matrix to find the coordinates of the vertices of the image, translated 6 units right and 2 units down. Then graph A, B, C, D and its image. All right? So the pre-image is the one that they give you. The image is the one when it is translated, which is what they're telling you up here in these definitions. So if they want to move it 6 units right, is that going to be an X or a Y movement? X. Is it going to be a positive or a negative movement? Positive. So in my X row, I am going to have positive 4s. Sorry, not 4s. 6s. Helps to write the right number. 2 units down, X or Y movement. Positive or negative? And then you would just add these two. So you would say, okay, if I add these two, I should get my new vertices. And we just did addition in our bell work. 0 and 6. Yeah, so we're just going to fill it in.
Are you always going to add them?
For a translation, you will. For a translation, you will. And I do want to point out that while your normal figure is A, B, C, and D, the image, so the pre-image is listed that way, that the image actually has these little dashes above it, and that indicates that it has been moved. All right? And so then you're just going to plot your points, and you are going to graph it. I'm going to make this guy. You want to label it, so we're going to say 0, 0, that's A. We're going to say -1, 4, that's B. -4, 2, that is C. And -4, 0, that is D. And then, of course, you are going to connect your lines there. So this is your pre-image. Your pre-image is the original one. And then they want you to graph your image. You're going to graph your image. When you label your image, make sure you put your dashes, because that's going to tell me which is your image and which is your pre-image. So we'll say 6, -2, that is A prime. 5, +2, that is B with our little prime mark. 2, 0, that is C, and 2, -2, that is D. And then again, you are going to draw your figure. Now, if for some reason you draw it and it looks like it is not the same figure, you may want to double check your coordinates or your addition and subtraction. because a translation should not make it move at all as far as skewing the size or shape. The size or shape should be exactly the same. So you should notice that everything's the same, the distance between the points, and the orientation is the same. So even the orientation will not change on a translation. For us here, it says a dilation is a transformation that changes the size of a figure. The translation does not, it slides it around. A dilation is a transformation that does change the side of the figure. When the center of the dilation is the origin, you can use scalar multiplication to find the coordinates of the vertices of an image. All dilations in the book are centered at the origin, so you can assume that your dilations are at the origin. They give us this example here at the top of page 189. An artist sends you a photo electronically. You increase the size of the photo by a factor of 1.2. The coordinates of the vertices of the enlargement, or find the coordinates. And they gave us the actual coordinates of the original. So they gave us the coordinates of 0, 0, 0, 5.875, 9.75, and 5.875, 9.75, and 0. And they want it on a scale factor of 1.2. So are they shrinking the picture or enlarging it? They're enlarging it, okay? And so this is what they would do to enlarge a picture. They would actually multiply all of the dimensions by a scale factor. The scale factor being what they want to change it by. And so if they do that, this is just like scalar multiplication, which is why it's called that. Scalar multiplication multiplies it by a scale factor. Dilation is when you change a figure's size by a scale factor. And so you're just going to use scalar multiplication here for dilations. You're going to multiply every piece of this by the 1.2, and you're going to find the new coordinates. And here they are. And you could plot them. And when you plot new points for a scalar, it's going to be the exact same size. It's going to be exact same shape, but a different size. So you will not have congruent figures like you did in a translation. You will have similar figures, all right? It will be different sizes. So you should get the same shape. If you don't get the same shape, you did your multiplication wrong for something, or you plotted your points incorrectly. But you should get the same shape, different size for dilations, all right? So they give you these 3 points, so it's a triangle. Find the coordinates of the vertices, and then graph. You only have one pre-image because it's the same one, but you're going to have 3 different triangles that you have changed. So go ahead and try check understanding number 2. All right, at the bottom of page 190, at the bottom of page 189, you see the definition of reflection. It is a flip or a transformation that creates symmetry on a coordinate plane. A reflection maps a point in the plane to its mirror image using a specific line as the mirror. The lines used will be the x and y axis, and the lines y equals x and y equals negative x. All right? And so on the next page, they give it to you. Now, this is actually with matrix multiplication. And so you'll notice that the reflection in the y-axis, which row is this, x or y? That's your x. So you'll notice the reflection in the y-axis is negating your x row here. The reflection in the x-axis is negating your y row, okay? Reflection on y equals x, you're actually flip-flopping your x and y's when you do this. And here you're flip-flopping and negating. And so you don't have to memorize the matrix piece of it, and like this, and you don't actually have to perform the matrix multiplication. But I want you to see what it does, and then we can write out some shortcuts for it. So look at the page 190. Look at page 190. So let's think logically about what reflection means. It means to come back, like make it symmetric across, really. And so we have y-axis here, symmetry. It's reflecting across the y-axis. My image here is 0, 0, and then we have 2, 5, negative 2, 3. So my image here is the black image. That's my pre-image. The pre-image here is the black one. The black image here is my pre-image. This is the one I started out with. You'll notice when I reflect across the y-axis, my y itself did not change, right? Did not go up or down, it stayed the same, but it flipped across and my x changed for every one of these points except the point that was actually on the y-axis itself. He did not move. And so they used matrix multiplication to do this. They took the negative 1, 0, 0, 1, and they did matrix multiplication across. But what happened? Well, my zeros didn't change. All of my x's went to the opposite. My y's stayed the same. And so when you are reflecting across the y-axis, all you have to do is take your matrix and negate your x. Negate your x. All right? You can do the matrix multiplication if you'd like to. I would personally write down negate x. That's what I would do, right? So then what do you think happens when you reflect across the x-axis? You negate your y, yes. Negate your y. It's not letting me. Come on. Negate your y. Let's look at y equals x. So first of all, what is y equals x? Well, it's this line right here, right? 1 slope, 0 y-intercept, this little perfect line here that hasn't been changed. And what happened here is we went from our original, our pre-image, and we flipped it across here. So let's see what happens when we multiplied. The matrix they multiplied by is 0, 1, 1, 0. What happened from the original matrix to the new matrix? You switch your x and y's. So you technically just switch those x and y's here. All right, switch x and y's. And then let's look at y equals negative x. Y equals negative x is that exact opposite line as a negative 1, right? What happened here? Switch and negate. So not only did they switch the x and y's, they also negated them. Switch and negate x and y. If I'm reflecting across the line y equals x, then that line is right here.
Oh, I thought you meant like x or y axis. Oh, I knew that.
Right? Right here. And it was originally on that line. So from the blue to the from the black to the blue, that reflection there, the reason C did not move is because it was on my line of reflection. So then if I cross the y-axis, anything on the y-axis won't move. If I am reflecting across the x-axis, anything on the x-axis won't move. And the same thing's true for y equals negative x. All right? The matrices for rotation. In this case, in your book, it will always be counterclockwise rotation around the origin. So that's very important. Counterclockwise. What does that mean? Counterclockwise. All right. So, and I need to double check on that, make sure it actually says that. Yeah, they're always going counterclockwise. So when you get your instructions from me, it'll actually say counterclockwise. Your book does not, because it always assumes it. But on your instructions, it's going to say counterclockwise. I just don't want you to throw it off. It just means that it's going the opposite direction of a clock. All right? Hence the term. So 90 degrees would then go from its starting point compared to the origin 90 degrees from wherever it was. 180, obviously, 270, one more 90, and then 360 all the way around. All right? So these are the matrices for those. If you look at the example on page 191, 90 degrees. We have 0 times negative 1, 1, 0. 0, negative 1, 1, 0. We are doing matrix multiplication. You will notice that the place holding switched. Okay, so we have our, instead of 1, 0, 0, 1, which would not affect it, we have 0, 1, 1, 0, and this specifically is a negative 1. So let's look at what happened here. We started out with 0, 0. Those didn't change. That makes sense. 2, 5. It went from 2, 5 to negative 5, 2. What did they do? They switched your x and y, and then they negated the new x, right? Negated the new x. So they switched and then negated x. So switch, then negated x. And that's what this guy does. You switch. Then you'll notice it is in order. Then you negate your x. Switch, then you negate your x. All right? You switch, then you negate your x. And you can see that it went from here and it went 90 degrees. And so if you were to actually draw this out geometrically, if you were doing this like with a compass and a protractor, you would actually create a 90-degree angle and measure that line and rotate it in that way. So not on a coordinate plane. If you were doing this without a coordinate plane points, you would create a 90-degree angle, and then you would actually measure it, that rotation, 90 degrees. So that's what they're doing here. Let's look at 180. You'll notice 180 did not move the placeholders 1001, but we did do something to them. What did it do? Right. So it negated what? Everything. It negated everything. It didn't switch anything. The order is the same. You see the order is the same, 1001, but it negated everything. So for a 180, you are simply going to negate your x's and your y's. Negate everything. Negate everything. Well, why would that work? Well, because if you start out here in the first quadrant and you go 180 degrees, you're going to end up in the third quadrant. This quadrant is positive x, positive y. This quadrant is negative x, negative y. If you start out over here in the second quadrant and you go 180 degrees, you're going to end up in the fourth quadrant. Well, second quadrant is negative x, positive y. Fourth quadrant is positive y and positive x, negative y, right? It's literally just changing it. You'll notice this guy didn't move. He's on the origin. All right, so anything on the origin when you're rotating around the origin will not move, just like in reflections. Let's look at 270. 270. Placeholders changed and they negated what? They negated y. So you'll notice they switched, then they negate the y. Switch, then negate the y. I would make flashcards or something if I were you, so you don't confuse these with the reflections. Because it's just a matter of memorization. And then 360 is really the easiest. What happens when you go 360? You end up where you started from, so it is the same. I know you want a quiz full of those.
Yeah, that'd be great.
Full of those. All right. Questions? All right, homework. Oh, so it did not update, and it says test tomorrow. So just see that coming up there. That'd be great. You'll be like, wait, what? Pop test, yeah.
Way to get me out of
Thanks. Suddenly I don't feel very well.
You're gonna be sick tomorrow.